Yes.
Okay. Okay, so hello everyone, and I'm Yifei, and I will be representing the Paris node as suggested by my very cliche background. I will describe some recent work of mine that falls into the first work package of this network about S-matrix Bootstrap, and in particular, some program that we develop out of this general idea that targets the strongly coupled gauge theories like QCD. Before I do that, okay, let me see. So before I do that, let me first give a brief introduction about the Paris group. The Paris group includes two CNRS labs. One is the LPTHE and the other one is LPENS. And there are 5 permanent researchers under this network in these 2 labs. You have heard some of their works in the previous talks, the Benjamin Basso, Gal Palos, Vladimir Kazakov, Emilio Trevisani, and myself. And so if you look at the network, it's a very big group in Paris. And so the topic covered here is also very diverse. But in general, I think the group are interested in developing perturbative approaches to quantum field theory that includes Bootstrap and integrability. And of course, there are special type of field theories that we're interested in. For example, conformal field theory, gauge theory, and also the closed-related holography. And in general, these approaches will be used to do computations about correlation functions, form factors, and scattering amplitudes. And so in this presentation, I tell you my current focus, which is developing this gauge theory Bootstrap program. This is a program that I proposed in the past year together with Martin Kruczynski in these 2 papers. And so the aim is to solve the strongly coupled harmonic dynamics of CD and similar gauge theories. And the idea is very simple, is to combine the modern Bootstrap technologies with the information from perturbative QCD. So in the following, since it's a very short and informal presentation, I'm just give a brief summary of main motivations.
If I can interrupt you, I think you are breaking a little bit. So maybe you can turn off the video and we see if we can hear you well.
Okay. Okay, so can you hear me?
Yes.
Okay, so yeah, I'm going to give a brief summary of motivations and the description of the approach, some initial results that we have obtained, and some process. So we're interested in asymptotically free gauge theory with NFs, and the theory is parameterized by a set of numbers. And what we would like to do is to compute the strongly coupled dynamics of the theory. This includes scattering amplitudes, form factors, correlation functions, and then extract from these quantities spectrum and couplings of the theory. And we would like to have theoretical numerical computation in the sense we're not using experimental scattering data as inputs. Assuming chiral symmetry breaking and confinement, the low energy part of it is dominated by the pseudo-Goldstone bosons, which are the pions. And there's a way to write down an effective field theory of the pions, which are parameterized by 2 universal low energy parameters, F pi and M pi. So the big picture we have of the theory is like the following. At very high energy, the theory is described by weakly coupled quarks and gluons and controlled by perturbative QCD. And at very low energy, we have weakly coupled pions, and there's an effective field theory description, which break down at some scale. But in the middle, we have a strongly coupled regime where there's no theoretical control. And the goal of the gauge theory bootstrap program is to connect all these three energy regimes and further gaining control of the strongly coupled regime. And we would like to use as the only inputs this set of numbers that define the theory. So to summarize the approach, which I'm going to give a little bit more detail later, there are three main parts. And I can illustrate it on the complex plane of the Mandelstam S variable. The central part is the modern S matrix and form factor bootstrap program, which allow to non-perturbatively parameterize the set of physical observables that automatically encode analyticity, crossing, and unitarity, which are the most generic physical constraints. At very low energy, we'll use the requirement from chiral symmetry breaking, which give us the prediction of the tree-level amplitudes for pions. And at very high energy, above some energy scale that we call S0, where we assume that the perturbative QCD works, we'll use the input from perturbative QCD through the SVZ sum rules and some asymptotic behavior of the form factors. So the general idea is to look for scattering amplitudes, form factors that first satisfy the most generic consistency conditions of analyticity, crossing, and unitarity, and in the meantime, match at low energy the prediction from chiral symmetry breaking, and at high energy, a perturbative QCD. So let me start from the central part, which is also a brief review of the modern S matrix form factor bootstrap program. So we are interested in several physical observables. The 2-to-2 pion scattering amplitudes, the 2 pion form factor of some local operator labeled by some quantum numbers, and the 2-point function of these local operators. And these physical observables have to satisfy the most generic consistency conditions of crossing and analyticity. So the program of S matrix and form factor provide a way to parameterize these quantities non-perturbatively that automatically satisfy these constraints. So for example, the scattering amplitude can be parameterized in this way, from where one can compute the partial waves. And the form factor can be parameterized by its discontinuity across the cut. And the 2-point function similarly can be parameterized by the spectral density. And so in this way, all these physical observables are parameterized by a set of bootstrap variables that we want to solve. And furthermore, there's a constraints from unitarity, which can be summarized into a positive semi-definite matrix like this for any physical value of energy and any quantum number. So this matrix allows to couple these different physical observables together. This bootstrap idea has a very long history, goes back even before the theory of QCD as an initial attempt to solve the theory of strong interaction. And so the main idea is to try to solve for these set of variables just from these set of consistency constraints. But as we know that this program did not work out in the old days, and today we understand why that's the case. Because there are actually a generic space of solutions to these set of consistency conditions. So there's no unique solution to the problem. But the modern S matrix bootstrap program put an interesting twist on this original idea, which is to maximize further some linear functionals of these bootstrap variables. And once we do that, we'll arrive at the boundary of this space of generic bootstrap solutions. This maximization problem has a unique solution, and so that explains why the modern S-matrix bootstrap program has a great success. And in particular, there has been many different explorations to use this bootstrap program to put bounds on physical quantities. An interesting result of this is that once one solves this maximization problem, there will be an extremal set of bootstrap parameters that describe the theory on the boundary. And from there, one can reconstruct the physical observables like the amplitudes. So this way, the bootstrap maximization serves as a way to do non-perturbative numerical computations. But of course, so far, everything is very general. And if we want to use this tool to solve some specific theory, we need to specify the theory that we want to solve. And the goal is to shrink this space to very small. So that brings us to the problem about gauge theory. And so the first thing we want to do is to include the information about chiral symmetry breaking. Chiral symmetry breaking gives us the low energy effective description of pions, and the tree level amplitudes give a very good description at very low energy. From this amplitude, one can compute partial waves, which are also very good, give very good description in the very low energy physical region. So in the gauge theory bootstrap, we numerically require that the partial waves in the bootstrap to match this tree level prediction in this very low energy physical region. And notice that how this can shrink the space of bootstrap variables, because these are additional constraints on the bootstrap variables. And furthermore, going to the high energy side, we need to specify the UV information through perturbative QCD. The first way to do this is through the SVZ expansion. Take the example of the vector current, which can be written in terms of quark fields like this, and consider its two-point function that in the large S that correspond to the short distance region is well controlled by perturbative QCD. Then we can consider a contour integral of a function like this along this red curve, which has to vanish due to analyticity. So the integration on the large circle at the energy scale S0, we can evaluate using perturbative QCD. And so this contour integral gives us some constraints on the spectral density in the low energy region, which becomes some sum rule about the moments of spectral density, which becomes constraints on the bootstrap variables. And furthermore, from perturbative QCD, we can also obtain the asymptotic behavior of the form factor. Suppose we have a vector 2 pion form factor, then using perturbative QCD, one can compute the leading behavior of the form factor at large momentum transfer, and it decays in this way. And so in the bootstrap application, we will just require that the form factor at large momentum transfer is very small. So that basically is the ingredient of the gauge theory bootstrap. And we perform some initial tests on this idea for NC equal to 3 and NF equals to 2. To visualize this, we can consider the space of amplitude characterized by maximizing some linear combination of two functionals. If one apply a generic S-matrix bootstrap, one gets a space like this. That's the space of amplitude that we have described before. So every point on the boundary realize optimization program. So there is an extremal amplitude there. Then by including the information about low energy from chiral symmetry breaking, the space shrink drastically, and further including the perturbative QCD information, one has a further smaller space. At this point, we can use the value of f pi at 92 MeV and the tree level amplitude evaluated for such functionals to identify some extremal amplitude as the result of our computation. So we can examine the extremal amplitude to see what we get. And so first, for computation up to 1.2 GeV, we can look at the GTB computation for the 3 partial waves, and in particular, their phase shift as a function of the energy. The red points are the Bootstrap computations, which compare pretty well with the experimental data and phenomenological fits that is indicated as the gray points and gray curves. And so in the S0, the experimental data has a kaon production that we can ignore in the 2-flavor quark case. And in particular, we see a rise in the P1 phase shift that should be identified with the rho 770 meson, which is a feature of QCD. And further extending this computation up to 2 GeV, we can check the computation about the first 6 partial waves. In addition to the rho 770, we also find a meson in the D0 wave that should be identified with the F2 meson. And also there are more mesons show up at a higher energy in the P1 channel. From these Bootstrap results, we can then extract many low energy parameters. This includes, for example, the threshold parameters like scattering length, effective range parameters, and also the low energy expansion about the form factor to get the pion charge radii. And further from these data, one can compute some Cairo-Lagrangian coefficients. And all of these compares reasonably well with the experimental data and the phenomenological fits of the experimental data. And in particular, the computation about the form factor can be plotted as a function of the energy. Yes, there's some questions or?
No, I think you can continue.
Okay. So we see first a peak that corresponds to rho 770 meson, and a smaller peak that we identify with higher meson. And this form factor fits very nicely with the form that has 2 poles in the complex plane in the standard Brett-Wigner form. From this fit of about the Bootstrap computation, we can extract these couplings and the spectrum information. And from this, we see that we basically cover some beginning part of the leading Regge trajectories of mesons. And hopefully by improving the program, we can see more at the higher energy. So to conclude, this nice agreement with experiments suggests that this gauge theory Bootstrap program might be on the good track for solving QCD. And the computation is very fast at machine precision. It takes about 20 minutes on an average laptop to get these results. And of course, we need to have a lot of improvement to make it more robust. So that's something that we're currently working on. And so the first goal is to really improve and refine the program, and hopefully we'll be able to put error bars on the computation so that it becomes some real non-perturbative computational tool. And in the future, we would like to be able to remove these 2 universal low energy parameters, fpi and mpi, and get it as a result of the Bootstrap computation to realize a real first principle computation of QCD. And then the program also allowed to change the gauge theory parameters, which will allow us to explore how the strongly coupled dynamics depend on these parameters. And so eventually we would like to be able to build this machinery where we can just tune a few knobs, and then the machinery will output the strongly coupled physics of QCD from this. So that's it. Thanks.
Thank you, Yifei. I think now we hear you well. Maybe you can turn on the video again.
Okay.
Yeah, you were breaking up a little bit and it was getting...
Yeah, my internet is not very good.
So are there any questions for Yifei?
Hi, Faye, can
Maybe
I ask one? Sorry, Francesco, go ahead.
no, please go ahead.
Can you tell us a bit about this matching to UV and IR? How is it done in the Bootstrap? And like you're using 3 levels, so maybe what do you expect? How would it change? How would the bound change with different methods of matching if you tried?
Okay, so for the UV is relatively slightly more clean, but we need to really improve on this more. But the idea is that there will be a alpha strong expansion. So so the imposing of the sum rule is not strict, but will be up to some error. And this error, for the moment, we estimated using this alpha strong expansion. And for the IR, well, right now, there is a numerical procedure to, we have a numerical procedure to do this matching by just, well, the point is that this matching at a very low energy cannot be exact, but has to be up to some error. And for the moment, we have a numerical procedure to determine this error, basically using FPy. And I mean, I'm not going to give too many details about it, but I think this is one of the main things that we have to improve in the future to understand this matching. Yes.
Thank you.
Thanks.
Maybe I have a question.
Mhm.
So you mentioned, Yifei, that you ran the numerics for 2 flavors, right?
Yes,
So
yes.
applied also to the other plots that you showed, or
Mhm. Yes, all these are for 2 flavors.
so do you have an understanding whether how these plots change whenever you change the value of ncolor and nf, or do some data?
So this thing, the changing the gauge theory parameters we can do now, but I think for the moment we're focusing on the 2 flavor case for the ability to compare with experimental data and to improve our program. And once that becomes more robust, I think we can use this to explore other gauge theory parameters, because if we change it to 3 flavors, and I guess we can explore the case where the mass of the strange quark is the same as the other 2 or not, and to determine whether we want to check more comparison with experimental data or to just do a pure theoretical study. But there will also be more comparison with lattice computation in the future, hopefully.
Thanks.
Thank you.
I had a small question on, so there's this, it's very nice the philosophy that you have where you in practice try to input as least information as possible, and the final goal would be just from the UV. This is very nice. But I was wondering, there's also this other direction of Kalian, Ning, and Andrea, where they just impose stuff from the IR, but a lot of it's more like doing a fit, seems, of experimental data. And for what I've understood, they have a problem in controlling the UV. But in your method, instead, it seems like you can input stuff from the UV, and you could also input the IR. Could you improve on their work?
So our goal is this minimalist approach to really solve QCD. But of course, this idea of combining this theoretical information, one can consider using it for phenomenological purposes and maybe improve the fitting with the data and all that. But personally, I'm more interested in this first direction. Yeah.
Yeah, it's very nice.
Thank you.
Okay, let me say that we come back in the afternoon with the 2 talks and the discussion, where if there was some questions related to the presentation, we can also discuss that. And so let's say that we resume in 1 hour. If that is do you think is enough time? Okay.